Now let's take a look at a quick demo showing how to use JOTS and refresh tokens to secure ASP.NET Core web APIs. We're going to use Postman to go ahead and log into our service just like we did in the previous demo. Once we successfully log in, we get an access token. And as we saw before, we can use that access token to access the resource. As long as the token has not expired, we expect to get back a valid 200 response when we access this resource. However, once a few seconds have passed, this resource will not be accessible because the token will have expired. As you can see, once the token expires, we get a 401 unauthorized. Now, normally we would have to log in again, and so some client of this API would have to redirect the user to re-enter in their email and password. However, because we're using refresh tokens, the client of this API can use the refresh token to get a new access token without the user having to be involved. To do that, they take the refresh token from the login request and send it to the refresh endpoint along with the email that was used for that token. In response, they get a new refresh token and access token, which can be used to, again, access the resources they're authorized to access. Now, if we need to revoke user access, we can do that by revoking their refresh token that was last issued. Once it's been revoked, it will no longer be usable for a refresh. Which means that if their token has expired, they will have no way to get a new one, and they will need to log in. If their account has been suspended, which is likely if their token has been revoked, then they will no longer be able to log in, and it will stop their access to the resources. Refresh tokens are created along with the access token. However, checking to see whether a refresh token is available is done using this code inside the authentication service. First, it calls out to a token handler, which will check and see if a singleton list of tokens that it's keeping track of has a token that includes the email address and the refresh token that were specified. This is the code that accepts a refresh token and confirms that it matches both the token and email, and then removes it from the list because it's been used. You can only use each refresh token once, and it returns back a refresh token. Once that refresh token has been returned, a new access token is created for the user, and then a new token response is returned. Revoking a refresh token simply removes it from the list and then ignores the response that comes back. I hope you can see that when you combine JOTS with refresh tokens, you get better security because you're able to frequently check and see whether or not the user's account has been suspended or the refresh token revoked, while not requiring the user to log in frequently, which yields a better user experience. While tokens are the most common approach to securing APIs, there are other options available which may make sense in some scenarios. One option that you can still use if you're running on Windows machines and strictly operating within your company network is Windows authentication. This can simplify security in many scenarios and should require minimal setup. Another option is to use cookie-based authentication to a backend for frontend server, or BFF, which is supported by Duende Software's identity server as well as other vendors, or you could roll your own. This approach is also known as a token handler because it still uses tokens, but they're not exposed to the browser. Instead, the browser application talks to the token handler BFF server, which in turn communicates with the actual API server. Using cookie authentication or ASP.NET Core identity alone is not recommended for web APIs, nor is storing tokens in browser storage where malicious scripts may be able to access them. The BFF token handler approach is best suited for single-page applications for these reasons. To configure your API to use Windows authentication, you must add the Microsoft.ASP.NET Core.Authentication.Negotiate package to your project and then configure your services with the options shown here. First, add authentication and specify negotiate defaults and then add negotiate. Next, by setting the default policy as the fallback, it protects all parts of the API. After building the app, be sure to remember to add use authentication followed by use authorization at the appropriate point in your HTTP request pipeline. With these options in place, your app will use Windows authentication. With the token handler BFF pattern, the client logs into the BFF server, which in turn authenticates with an authentication server, sometimes called a secure token server or STS. If successful, the BFF server receives a token, which it stores for later use, and returns success for the login, sending a header with the ASP.NET Core Identity Authentication cookie. Now, the client browser manages the cookie and automatically applies it to additional requests in the same domain. The client can now make an API call to the BFF server. The cookie ensures that it is a known authorized client, and so the BFF server makes a corresponding call to the API server, passing the token that it had previously received and stored. Using this approach, tokens can be revoked at any time, since the BFF server is controlled by the organization managing the APIs, which means longer expirations can be used for the tokens, and there's less of a need to implement something like refresh tokens. You can learn more about this approach from Duende Software as well as Curity.io's article on the token handler pattern. We've already seen a few different ways to configure authorization and authentication with ASP.NET Core. In this section, we just want to highlight a few important practices. Before building the app, configure required services for authentication and authorization. The order of these typically doesn't matter, but authentication is typically done before authorization. Shown here are the options used to configure Windows authentication. Different authentication schemes can require varying amounts of configuration. This example configures the scheme using the JOTBearer default .authentication scheme. Next, it calls add JOTBearer to configure some typical configuration parameters that may be specified when configuring JOT security for an app. Note that you want to make sure that you're validating as many parts of your JOT tokens as you are able to. It is possible to configure more than one scheme for a given application, in which case you can specify which scheme to use for a given endpoint using the authorize attribute. This example configures both cookies and JOTBearer tokens. On the left is a controller that has been configured to use JOTBearer authentication, while on the right, the controller there is configured to use cookie authentication. Both options need to have had services configured, and it's possible to support multiple by passing a comma-separated list of schemes to the authorized attribute. You can even specify multiple schemes for the same kind of authentication. For instance, you might need to accept tokens from users who authenticated with one of a variety of different services. This is supported, but you must ensure each scheme has a unique name. In the example shown here, the second JOTBearer scheme is named Azure AD. Take care that you're adding your authentication and authorization middleware and that you're doing it in the proper order. Authentication lets your app know who the user is. Authorization ensures that known users are only able to access things they have permission for. You need to make sure they are used in the correct sequence, as shown here, with authentication always preceding authorization. Another feature built into Microsoft.ASP.NET Core.Authorization is support for policies and imperative authorization. Policies provide named sets of authorization rules, which can include custom code through the use of requirements and handlers. In this case, the edit policy is being defined to have a requirement of type same author requirement. You can see that this type is just an empty class that implements the iAuthOrization requirement marker interface. However, the class name is important because it will correspond to a handler that is used for this policy. By defining a handler that takes in the requirement type along with the resource that it's protecting, you can create custom logic that determines whether or not a given operation should be allowed to proceed. In this case, the handler checks to see if the current user's name matches the document resource's author name, and if so, allows the operation by returning context.succeed. Let's look at a quick demo showing how to use imperative security policies with an API. We'll start by looking at how the application is configured. Here, you can see that we are using Windows authentication, where we have specified Negotiate Defaults Authentication Scheme and Add Negotiate. We've also configured a few policy handlers. You can see we have a Document Authorization Handler and a Document Authorization CRUD handler. The application uses a document controller to let users look up a document. However, users are only able to access documents that they are the author of. The only endpoint that is exposed is a GET action, which tries to look up the document, and then if the document is not found, it will return a not found result, but otherwise, it will check whether or not the user is authorized to access this document. It's going to use an operation.read to check to see if the read operation is allowed, and then it will authorize that user and return back if it was successful or false otherwise. Then we will return the document if they have access, or we'll return unauthorized otherwise. For this simple demo, we can specify any author name we want inside the repository itself. We aren't using any real data, we're just specifying the information here. So for instance, since this is Windows authentication, if you are not on a network, you would just use machine names /username. If we debug this application as it stands now, we don't expect that it's going to work because my username is not machine name /username. Another thing to point out is that if you're using a guest browser, it's not going to carry forward your Windows credentials. So even if you are logged in and you've specified the correct author, it will not work. Just to demonstrate what we get when things fail, this is going to ask us to log in because of the fact that we're in a guest browser. Using another browser where we're not guest, in this case Edge, we should have a different story. Now you can see that we have hit our breakpoint where we're performing a CRUD operation to try and read this document. The resource author is expecting machine name username. However, I'm logged in as Steve Lenovo Steve. When we step past this, you'll see that we get a 401 error unauthorized. Let me go ahead and correct the repository to use my username. Now we'll start the application again. This time, we'll go ahead and start directly from Edge, and we'll just re-execute our operation. You can see that now I am Steve Lenovo Steve, and the author resource is Steve Lenovo Steve as well. Continuing the operation, we get a 200 status code with the document that we expect. The main point of this is that you're able to create imperative security policies using handlers that will be able to access your database or your business logic as part of your authentication flow, rather than having to do everything just using roles or claims that are specified in the user's token.